Okay, so we're starting class and you guys were looking at doing a try it. So if you didn't come to class today and you're joining by watching the video, I want you to pause the video and take a moment and try this and work it out and write it up. I may ask you to turn it in for participation points. And so students worked on this and they then went on to breakout rooms and tried it or made sure they got things right and discussed it. So now we're going to take a moment and go through these really quick. So for the first one, when you're looking at the limit as x is approaching 2 of 2x squared minus 11x plus 14 all over x squared minus 5x plus 6. And so you should have done was direct substitution. And so wherever you saw an x in your equation here, you would go back and substitute in 2. So doing that, I would have 2 and then squared minus 11x plus 14 all over 2 squared minus 5 times 2 plus 6. And so if you simplify that down, you should see that you get 0 over 0. And so remember if you get 0 over 0, this was an indeterminate form and this didn't tell us anything about the limit. And we needed to go back and we needed to manipulate it so that it wasn't in that form anymore. And so one way, if you have a rational function is, and it's a polynomial divided by a polynomial, is to try factoring it. They both have common factors in the numerator and denominator. Okay, I'm going to see if I can do this with trial by error. I know.
Do you need help?
Is it -2 and -7 and a -2 here? Is that right? -7?
No, -7 with the 2x.
Okay. I would have FOILed there in my head and see. And then x minus 2?
Yes.
Okay, so then the next one, that's going to be probably a x minus 2.
There's no 2x on the bottom one.
Okay. Sorry. Oh yeah, there's not. I thought that was a 2 in front, but that was my 2 for my limit. And so that is a -2 and a -3.
Correct.
Thank you. Oops, thank you. And so notice we have common factors, which we thought we did because of 0 over 0. And so now if we go back in and wherever we see an x, we replace that with a 2. And so we have 2 all times 2 minus 7 all over 2 minus 3. So 4 minus 7, that's -3. And then 2 minus 3 is -1. So you should get 3. So this problem here is the exact same thing happens. You get 0 over 0. I'm going to actually skip that one. Does anyone want to share what they got so if someone else didn't get it, if they want to work through it?
I got 2.
Anyone get something different than 2?
I got 10.
I got 10.
Okay, well, maybe we should go through.
Oh. No, I think you guys are correct.
Who do you think is correct?
I think the 10 was correct.
So to your
Wait, no, never mind. I think, sorry. I think it's 2. Sorry.
Okay. So let's look at this. So does that mean the people who think 10 said 10?
Yeah, 10.
10. Okay, you're still holding on to that number. Let's see who's right. Okay, so we have the limit as x is approaching 4. And we get 0 over 0. So again, let's rewrite it so that we're factoring this. So I know I need a 3x on 1. I need an x on 1 to get the 3x squared. Okay, help me out here. What were the two values? 3x
Plus 8 and x minus 4.
plus 8 minus 4. Okay, so that's just, let me just check it. So 3x squared plus or minus 12x plus
I think it should be minus 8 and plus 4, right?
minus 8.
No, it's plus 8.
It's
Oh,
But on the
wait.
thing, it says negative 4. So I
Oh,
think I
you're-
messed up too.
You're right. You're right.
this right here would give us the negative 12x, and this right here is going to give us the positive 8x, and that would sum to the negative 4x. And so that's where one of you guys might have gone wrong and got either the 2 or the 10 by factoring it with opposite values there, signs. And then the bottom one, which is nice because that it doesn't have a coefficient of 1. So it adds to 8 and or add to negative 6 multiplies to 8 is a negative 2 and a negative 4. So the x minus 4s cancel. And so now when we go back in and we plug in 4 wherever we see an x and what's left, we have 3 times 4 plus 8 all over 4 minus 2. 3 times 4 is 12. 12 plus 8 is 20. 4 minus 2 is 2. 20 divided by 2 is 10. So I believe the 10s have it.
Oh, yeah.
So it was probably that just little that we were off by the factoring. You had the right process, knowing you had to go in and factor, and you thought you had done it right because, you know, it came out with a number after that. That was where the factoring was. So the next one, W3, W4, W5 here, the warm-up. These are really important when we're looking at the limit, and this is something that we're going to talk about today when we're looking at continuity. And when we're looking at continuity, meaning it's continuous at a value, x goes to c. If we're looking at a piecewise function, it's important to look at where it's changing values, the end values of your inequality. So the end values where the equation is changing. And we know that a limit exists if the left and the right are equal to each other. So notice that this one where you're looking at the limit as x is approaching 3 of f of x, 3 happens to be a value where we're using the left-hand first equation on the left, and we would have to use the second equation if we were looking at the limit as x is approaching 3 on the right. Let me see. I'm going to just bring this down so I have some more room. Okay, so let's look at the limit as x approaches 3 on the left-hand side. So this means I'm putting in values of x which are less than 3. And so values of x which are less than 3 tells me that I need to use this first equation, x plus 1. And so when we go in here, we're just going to go back in and plug in 3 wherever we see an x in this equation. And so we get 3 plus 1, which gives us 4. Now we want to look at the limit as x is approaching 3, though, on the right-hand side. And so on the right-hand side, we have values of x which are bigger than 3. And it tells us that we're using this equation for x that are bigger than 3 and smaller than 5. So that's telling me that I need to look at this equation here, 2x minus 2. So same idea, we're going to go back in here, and wherever we see an x, this time we're going to plug in 3. So 2 times 3 minus 2. So this gives me 6 minus 2, which is 4. So since these are the same values, we know that the limit exists. So the limit as x approaches 3 of f of x is equal to 4. If we had gotten different values when we had done this, then it would not have existed. So you want to do the same thing with this one. And we're looking at the limit as x is approaching 5. But if you look at this number 5 again, and I go in here and I look at, okay, where does 5 fall for this piecewise function? Again, it's an n value of my inequality. And so I have to be careful here because I'm changing equations at that value. And so we want to look at what's happening as x is coming in on the left. So 5 for that little. So left, that's telling me I'm plugging in values which are less than 5, which tells me to use the second equation, which is 2x minus 2. So if we go in here and plug in 5 wherever we see an x, we have 2 times 5 minus 2. 10 minus 2 is 8. Now looking at the limit as x is approaching 5 from the right, well, this is values of x which are greater than 5. So numbers greater than 5 tells me that I need to use equation 3, which is 4x plus 1. So plugging in 5 wherever I see an x there, I got 4 times 5 plus 1. 4 times 5 is 20, plus 1 is 21. So here's an example where these are not the same values. And so we know that there's a jump in the graph. We're going from a y value of 8 on the left to a y value of 21 on the right of 5. We could say that those, if we were just looking at a left or a right-hand side limit, we would say those exist and they are going to values, but the limit itself does not exist. And we talked about left and right-hand side limits or one-sided limits in the last couple of class periods. So the limit as x approaches 5 of f of x does not exist. Last one is actually not as hard. So we want to look at the limit as x is approaching 6. Well, if you look at this again, go back up to your piecewise function and look at which equation it tells you to use. 6 falls into this third equation, but x is greater than 5. We're using this for this third equation. And so basically for the left and the right, because this is not 6 is not the n value of one of our inequalities, we just have to look at this equation. So we don't have to worry about left and right changing values. And so we're just going to use this. So limit of x approaches 6 of 4x plus 1. Plug in 6 wherever you see an x. So 4 times 6 plus 1 is 24 plus 1 is 25. Okay, so hopefully you found out if you did it right. If you didn't do it right, hopefully you saw that, yeah, I do understand the concept. I just accidentally factored wrong, or you understand where you're missing that concept. Maybe this is a great time to ask you any questions.
How do we turn it in?
Okay, so since I pretty much went through it all, I probably won't have you guys turn it in today. But sometimes I will do that like an in-class exercise and we might not have time to go through the whole thing. I would create an assignment on Canvas and I would just say, okay, turn in the in-class exercise you guys worked on today and upload it. I might ask those students that didn't show up to lecture today to make up an in-class exercise to make up points for not being here and working on it during class to get participation points. But for all of you that are in class right now, you don't have to worry about that.
Okay, so should we just keep all these try-its for the notes for today as well?
Yes, please. Yeah, so just keep these in as your notes. And so again, there might be a time in the semester where I'll say, hey guys, I want you to show me some of your lecture notes, and I'll just randomly choose some dates. Same thing with the written work for my math lab. I might say one day, okay, I want to see how you're writing up your homework. Please turn in this section and this section. And I'll probably just randomly do it. And I'll give you points for turning it in and writing it up correctly.
So we're supposed to save all of this, and just for clarification, because I'm not much of a kinesthetic learner, and I'm not the fastest writer. Yeah, right. I need to write down all of this so that I can so that I could just have this at the ready.
So if I don't know how you're right. All of us are different types of learners, and some of you might be better at just sitting back right now and watching and not even really taking notes. And so, but when you're that kind of a learner, do you have to go back and kind of, jot down stuff?
Oh, I'm a visual learner. That's why I just watch and then I'll get the concept.
That's cool. Okay, so maybe just writing down the important parts from that day and the concepts that you would have gotten from there, or like the important, like in today, continuity. Okay. So this is something I might ask you or show me that all three of these steps hold, showing that something is continuous. So this is something that you might want to have written down.
All right.
And so just keep like a notebook, or however you guys keep things organized, of your notes from class and your notes from your homework. Okay, so continuous functions. We're looking at what it means to be continuous at a value x equals c. And so if you remembered from maybe college algebra, we basically said something was continuous if you could draw it on a graph and you didn't have to lift your pencil or pen to continue to draw the function. And so there's multiple examples of how something can be discontinuous. So if it's not continuous at a value x equals c, then it's considered to be discontinuous there. So let me give you a couple examples of what that might look like. But actually, before we do that, let's look at the conditions. All these conditions must hold if we're looking at and showing that something is continuous at some value x. And so first of all, if it's continuous at x equals c, we must say that it is f of c is defined. So that value is in our domain, c is in our domain, and we get back some real number. We also have to say that the limit as x approaches c exists. So remember, that's a key point that we were just talking about. So for the limit to exist, recall you're going to need to show that the limit as x approaches c on the left of f of x is equal to the limit as x approaches c on the right of f of x. And then the last thing that you need to show is that when you look at the limit as x approaches c and you just plug that in, you'll get back what f of c is. So they're the same thing. Your limit as x approaches c is the same value as the point that exists on the graph f of c. So basically, if you can show one of these conditions does not hold, then we can say that it's discontinuous. If we can show all three of these conditions hold, then we can say it's continuous at that value. Okay, so you might have some graph and you might have a little circle here, and then it continues on. So notice that this is discontinuous at x equals c. Maybe we actually even have a closed circle up here. So in this case, if I looked at this and I looked at, well, does f of c exist? It does. Oops. F of c exists and it's equal to our y value at that point m in this case. The limit as x approaches c on the left, we're getting closer and closer to this value of L. Let's call this f of x. And if I look at the limit as x is approaching c on the right, I can see that's the same value I'm approaching, even though it's not defined at CL. So the limit exists. Okay, so both those conditions hold, but notice in this case, my L is not equal to my M value. So this is a case where number 3 doesn't hold. So the limit as x approaches f of x is equal to L, which does not equal, oops, x approaches c of f of x. Equals L, which does not equal f of c. So because of this condition, the graph is discontinuous or not continuous at x equals c. If this was just undefined there, maybe you have the exact same graph, except instead of that point at CM, there was just not defined. I don't know if I can do that. That's wrong. So let's say we have pretty much the same exact graph. But here we didn't have this point. We can see that it's still discontinuous at C. The one thing that doesn't hold in this case, well, two things that don't hold. F of C does not exist. And in order for it to be continuous at a value, it has to exist. But this is a particular discontinuity that is helpful because it's called a removable discontinuity. So in this case, if I have this where it's undefined maybe at this point, I can say, well, let's just put a point there. Let's just define it. When x equals c, we're going to call that L. And so we can call this one as a removable discontinuity. By defining x equals c to be up. And so when we do that, now we put in this point CL in here, now it's closed, and now it's continuous. Where it was before. But not all of our discontinuities can be removable. And so that's a special case. Cases where it's not removable would be where you had a jump in a graph. So a piecewise function where it's changing values at some x value and the equation changes, your y values are different. So something like this. So this would be called a jump discontinuity. The others we have are asymptotes. And so recall, and it will be helpful if you don't remember how to graph rational functions, to go back and review that and recall how to find a vertical asymptote and a horizontal asymptote of rational functions. That's going to be helpful for you. I'll quickly remind you when we go over that piece, but when you have a rational function and you have a value that sets the denominator equals 0, but not also the numerator, those are where your vertical asymptotes occur. And so you might have some graph that looks like this. And a graph can never cross a vertical asymptote. We denote that vertical asymptote usually with a dotted line or with a dotted line, but it's really not on that graph. And so here's an example where this is a discontinuity because of a vertical asymptote. We also saw one the other day that was kind of unusual. That's where we looked at sine of 1 over x and we went and looked at the graph of it, and it was oscillating really, really fast between -1 and 1 as it got closer to x equals 0 on the left and the right. That's another example where a graph would be discontinuous. So we saw something that came in, and then as it came in here, it just went back and forth really fast. Okay. So an oscillation or fast oscillation. I don't think I'm spelling that right. Is a discontinuity. We also saw that it was undefined at 0 anyways, at least the one that I'm talking about. If I was talking about y equals sine of the argument was 1 over x. And we can't have 0 in the denominator there. Okay, so those are the different possibilities that you would see where a graph is discontinuous at a value. And that is a perfect time to stop. So now you know what it means to be discontinuous, what it could look like, the rules that you need in order to show something is continuous or not. And then tomorrow we will look at some examples of graphs, of equations, of trigonometric functions, of compositions of functions, and continuity.